Okay, I'd like to do a video here on Charles Boyle's law and the combined gas laws. And I just want to show you a couple of things. First of all, here are the two laws. This first law here is Boyle's law. I'll just put a B there. And this is Charles' law. What Boyle's law is basically saying is if you have a gas, one gas, and you measure its pressure and its volume, these two things are related in such a way that if you change either the pressure or the volume, the product of the new pressure and the new volume for the same gas will be the same as the initial. What that basically means is these are inversely related. As the pressure goes up, the volume goes down. So as my P goes up, my V goes down, and that means the product of these conditions will be the same as the product of these. Charles' law is set up so that the volume, an initial volume, and you notice I'm showing like, 1 is my initial and 1 is my initial here. The ratio of these would be equal to the ratio of these in my new conditions. So if I take some initial volume over an initial temperature, and by the way, very important point, this must always be in Kelvin. In all of these sorts of problems, you must put your temperatures in Kelvin. But what's going to happen is as the volume goes up, I'm sorry, let me say it this way. If I take the volume and divide it by the temperature, change either the volume or the temperature and divide them, this ratio will be the same as this ratio. And what this means is that the volume and temperature are directly related. That is, the temperature goes up, the volume goes up. And most of you know that. As you heat a gas, it's going to expand. As you heat almost anything, it expands. And as you cool it off, it contracts. So now let me show you what problems would look like with this. Here I have a situation where a gas occupies a volume of 458 milliliters at a pressure of 1.01 kPas and a temperature of 22 degrees C. Now if I need to use temperature in my problem, I'm going to have to right away turn that into Kelvin, but I actually don't in this problem, so we'll just keep going. The pressure is changed, so I'm changing the pressure and the new volume is this 0.477. If there's been no change in temperature, which is why I don't have to worry about this, what is the new pressure? So this is a thing where I have a volume and a pressure. I am changing the volume. What's the new pressure? So this is going to be a Boyle's law problem, and my initial pressure and volume are listed here. So I have my volume is 458 milliliters times 1.01 kPa, okay, will be equal to my new volume. Now if you notice, this is in liters, so remember milliliters and liters, the relationship is 1 to 1,000 or 3 decimal places. So 0.477 liters is 477 milliliters. These have to match. You could have turned this into 0.458 liters or you could turn this into milliliters, and it does not matter, but they just must match. And this is going to be times, and then what I'm solving for here is my P2. So as I've set this up, basically I just need to multiply these two numbers, the 458 and the 1.01, and then I'm going to divide that by the 477. And when I do that, I'm going to get my new pressure, which will be in kilopascals, because remember, my units are going to match. And if you do that with 3 significant digits, I believe you're going to get 0.970 kPas. So that would be my new pressure. So again, really all I did, I call these plug and chug problems. I plugged in my initial pressure, which was this one. Here's my P1, my initial volume, my second volume, and then I just simply solved for my new pressure. And then I got this answer here. Now the second part of this question is, what is this pressure in millimeters of mercury? If I ever have to do a conversion, it's pretty easy. All you do is you go 0.970 kPas times in a line. The units you begin with always go in the bottom of the next fraction, and then whatever I'm going to goes on top. And this is, what do they want, millimeters of mercury. And again, you need to know the relationship between these numbers then. And with my students, I give them a reference packet, and in there I've listed that 760 millimeters of mercury are equal to 101.325 kilopascals. So then what you do is you just take your calculator and you take the 0.970 times 760, get your answer, and then divide that by 101.325, which I'm actually doing as we speak, and I got 1.325 on my calculator. I'm allowed 3 digits because of this, so I'm going to round that to 1.33, and that is going to be in millimeters of mercury. And so that would be my correct answer. So, depending, most problems in my class and the tests and things would look a little more like this. Would be kind of a one-step thing. This is a second step where you're doing a conversion. This is a similar problem. It's called Charles' law. It's the same idea. You're going to be given an initial temperature, and then here is a, oh no, I'm sorry, this is the second temperature. Here's your initial temperature. Here's your initial volume. Assume the pressure is constant. So again, my P doesn't come into play here. So what I'm going to end up doing is my initial volume of 3.42 liters, so I'm plugging that in, over my initial temperature of 215 Kelvin will be equal to my new volume, which is what we're trying to solve, over my new temperature, which is 309 Kelvin. And again, mathematically, what you would want to do is, of course, multiply both sides by 309. And then what's going to happen is these will go away. So now I take that 309 times my 3.42, divide that by the 215, and you're going to end up with 4.92 liters. And if you think about it, that should make some sense, because what I did is I had a gas at 215, I heat it to 309, the volume should go up, it should expand. And so then that would be your correct answer. Now what also happens is we can combine these two laws, this Charles and Boyles law, into what is called the combined gas law. Some people call it Choyles, or you hear kind of silly names and stuff, but basically you're left with P1V1 over T1 is equal to P2V2 over T2. Again, it's a plug and chug problem. There's just more variables that I'm plugging in here, but you just kind of fill these things in and solve for the problem. Now the example problem that is given to you here is that you've got a sample with this volume, 2.88 liters, this temperature, and this pressure. At what new temperature, and this is going to be in Celsius, would it have this volume and this pressure? So let me kind of write this out and we'll just fill this in. P1 V1 over T1 is equal to P2 V2 over T2. And then let me just fill these in. I'll use a different color as I do this. What's my initial pressure? My initial pressure is 655, and this is in millimeters of mercury. My initial volume is given to me as 2.88 liters. My initial temperature is given to me as 73 C, but as I mentioned a moment ago, you must always in this unit do everything in Kelvin, and so if you add 273, you're going to get 346 Kelvin. So that would be my new temperature. Now they want to know at what Celsius temperature, so I'm actually solving for this. Now my answer will be in Kelvin, and I'll have to convert that in a moment, but we'll get there in a moment. My new pressure, or I'm sorry, my new volume is 0.553 milliliters, but 553 milliliters, but you have to make sure your units match. So as I said a second ago, that's 0.553 liters. And my pressure is given to me as 2.47 ATMs. The only problem is this pressure was in millimeters. So I am going to have to convert that. Let me do that maybe in a different color as well. So what I'll do is do 2.47 ATMs times in a line. I'm going to put ATMs down here, and to make them match, I'm going to go to millimeters of mercury. So that's going to be 760 millimeters for 1 ATM. And when you do the math here, you're going to get 1877.2. And that's millimeters of mercury. Now, you could round this, and you probably should at some point round to 3 digits, but for now, since I'm plugging this into this other problem, I'm going to put it in and not round it. So that would be 1877.2, but I'm recognizing that that is only good for 3 significant digits. So now this is why I call it a plug and chug. I've got a bunch of numbers here. You could actually multiply and divide all these and get a number. And then this is my variable that I'm solving for, and then there's some numbers up top. If you actually do all this and solve this, I think you get 100, if I did this right, I think you're going to get 190.40. And again, that is unrounded, of course, and that is going to be in Kelvin. They want this in Celsius, so to go from Celsius to Kelvin, I have to subtract 273 from that, and when you do that, I believe you're going to get negative 82.6, and then that is going to be a degree C. So again, that's all you're doing. These gas law problems, Charles Boyles or the combined gas law problems, you're simply going to be given all of the conditions except for one. In the problems that we just did a moment ago, there were basically 4 variables. I gave you 3 of the 4. In this new problem, there are 6 variables, and you'll be given 5 of the 6. And then you're just simply solving for the one you don't know. remembering to always put your temperatures in Kelvin, or recognize that they're going to come out in Kelvin, making sure your units match. Notice how I had to convert the volume and the pressures to make everything match. All right, I hope this helps you.